Hello, guys. If you haven't already done so, please turn your cameras on so that I may remember what you look like. And you all have received the exam, am I correct? You all are aware of the exam having been posted. And how are the questions coming along? They're not coming along? All right, so just you can easily solve a question per day and try to be aware of the question so that, yes, you submit through email, you understand which format, correct? You title the exam as E, last name, first name, exam 1. And just so that you don't write E, last name, first name, I gave an example of, of what you should put there, right? So if it's Ting Jiang, then it's E Jiang Ting probability exam 1 or something. You can just write exam 1. I know that your probability from the first letter. I said not E, sorry, I said P. Right? It's for probability. Good. Everything's good. And again, guys, I repeat my request, turn your cameras on if you can. The more people I can see, the more I feel like I'm talking to someone. And now let's quickly review what we talked about in the last class. Guys, if you ever need more time, you understand you can stay after the lecture, and I'm happy to re-explain anything, and I'm happy to go much slower than what I do here. So I hope that you understand that it's a bit difficult to give you just enough time for everything. So let's just briefly remember the concepts that we covered. So very, very important is the concept of conditional probability. So that's the probability of E given F. That means that we have knowledge that a subset of all possible universes has taken place. In other words, one universe in particular has occurred, right? So for instance, I could have been giving lecture in so many rooms. The room could have been colored white, green, yellow, right? If I know that the room is either white or green, that's the event F. I know something about the possible universes. I might not be aware which specific universe happened, but I am aware that a certain collection of universes must have occurred. One universe in that collection has occurred. Is it understandable? So for instance, I threw 2 dice and the sum is 7. That means that I'm in universe 1 and 6, or 2 and 4 and 5, and so on, right? That's what F is saying there. And then we want to know the probability that some other collection of universes with particular property occurs. And we know that this probability is the same as the probability of E intersect F divided by probability F. Now, just before I continue, just would you honestly tell me with something like Y or N, how many of you believe that you understand how this formula came around, or at least some explanation for it? How many of you think that you understand why the formula is true, and write Y or N if you are Y for if you understand if it's true, something like that. Very good, right? So hopefully you can explain it in so many ways. One of them is the frequentist explanation. Frequentist explanation will mean that what are we really examining here? So this the probability that E occurs given F, it is the limit where the number of outcomes that look like F goes to infinity of the number of outcomes in E and F divided by number of outcomes in F, right? So the reason we take intersection is because if, well, the property E might have universes outside of universes in property F. Does it make sense? So E and F, E might not be a subset of F, but if F occurred, I cannot consider universes outside of F. So I take the intersection to account for that. Yes. And so I just do the same idea. That's in terms of outcomes in F, how many times do I have E occurring inside of such outcomes? And then, of course, this is the same as limit of overall trials, where I divide by total number of trials in the space S, which is just then the outcomes in EF divided by N divided by the outcomes in F divided by N. You see, I did not change the fraction, but this gives me numerator. It's the probability of EF divided by probability F. Just hopefully that gives you a sense of why this is true. Just I know many of you said yes, but I just want to emphasize, you really have to think again and again to be sure that this formula is not just something that you use, but something that you truly understand. Now, so be careful, right? There's a probability E given, okay, so you're conditioning, okay, P given F, you can change it, then you can write a bunch of formulas, you see, guys? So the advantage is that you sometimes can reverse the condition, right? So for instance, if I want to know the probability of E given F, that happens to be the same as probability EF divided by probability F, which can also be written, the numerator here can be written as probability EF divided by probability E and multiplied by probability E divided by probability F. Yes? And the numerator is simply the same as, look what I just did here. A numerator represents probability of F given E. Right? This is probability F given E by same definition times the probability of E divided by probability F, which tells you that you can just manipulate this formula to change if the condition that you have is not suitable, you're not able to calculate using it, you can reverse. You can assume that E occurred and you are trying to find the probability of F, but of course for that you multiply by the ratio PE/PF. Okay, by multiplying by the ratio PE/PF, as Rader noticed, I can just change what I believe happened and arrive at the probability. Good. So those are very important ideas, tremendously useful. And this also allows us to understand why multiplication occurs in probability. So if you took this class in statistics in high school, you might have been told multiply the probabilities. But why do you really do that? Well, for that reason, guys. Suppose that I want to understand the probability of A and B happening, right? Probability A and B happening means, well, that is the same as what? That's the same, I can just write as probability A times probability AB divided by probability A. Do you agree? I mean, assuming probability A is not zero, because if probability of A is zero, then probability of AB would also be zero. Do you agree? Because AB is smaller subset, and therefore it's even less likely to occur than A. Right? So, so this is probability A times probability AB times probability A, which is probability A times the probability of B given A. That's where multiplication comes from. Good? Yes? Apologies that there were some people asked something. I will maybe talk about it. I mean, I'm not sure if it's immediately relevant, but there are some 5 comments that I'm not so good at multitasking. I yet haven't fully processed them. So this is the situation, right? So what happens is that you can see that you multiply one probability by another. we're going to learn about independence. So in high school, mostly you assumed that, let's say, when you toss one coin and it's a fair coin, it does not affect the next toss, right? What's the probability of tossing twice heads, right? So first, let's say is 1/2 times 1/2. Now, why is it 1/2? Because first we have heads, the probability of that is 1/2, then probability of getting heads again, given that we got heads on the first toss. And because we're assuming that the coin is not remembering what happened before, the probability is still 1/2. We're going to learn and talk about independence later, but that at a much greater depth. But the idea is that you multiply probabilities because of conditioning. Good? Conditional probability. And there is nothing special about doing it with just two events. I could have done probability A, B, C, and that would be a sort of product, but not of probability A, probability B, probability C. That happens only on special occasions. It would be this product, guys. It would be the product. I can just write it like this: probability A, probability A, B divided by probability A times probability A, B, C divided by probability A, B. Are you in agreement? So do you see that everything here is telescoping? So for instance, this disappears and this disappears. So I haven't lied to you. Of course, if the denominator for any of them is 0, then the probability itself is 0. So in that special case, I'm lying to you very slightly, but those are not interesting situations. Yes. So in general, you can see this is what's happening. It's called a telescoping product. But then if I don't cross it out, what do I get? I get that this is probability of A times the probability of B given A, because this is just the definition of conditional probability. Do you see this, guys? This is the conditional probability of B given A. Yes. And then what is the remaining one? It's the conditional probability of C given AB. Yes. And you can just do that for any number of events. And we do that very frequently and without a pause sometimes. So make sure that you are good at such ideas. And let's go back to the lecture. Hope we are ready. So the next question is a little bit difficult. Remember, we solved one about medical tests and we solved one about lines. Now, the next question is a little involved. We'll see if you can understand it. It's a little bit, I'm not sure if my wording of it is very nice, but I'll try. So, okay, here we go. Now, this one is still not too bad. In an ongoing investigation, the inspector is 60% certain that the suspect is guilty. So do you understand the sentence, guys? How do you process this sentence? I can tell you how I think of it. I imagine a universe, right? Basically, I imagine a collection of universes where different people are guilty. In 60% of those universes, this particular person, Jimmy Jones, is guilty. You understand how I'm thinking of it, right? So I imagine parallel worlds. Like, I'm not sure, there used to be this movie called Sliders, or I don't know, what else is there? Doctor Who, where you go to parallel universes. So in 60% of those universes, this particular guy is the bad guy. Well, right there. Well, I do not know. You left-handed people are naturally guilty. Always. So, I mean, at least if they have girlfriends, trust me, the girlfriends will, I'm not sure, left or right-handed or anything else, they will just suck your life out of you. So, yes. So, 60% are guilty. Now, we know that the criminal was left-handed, right? Left-handed criminal, for sure. We just do not know if this particular guy is left-handed or not. But maybe I should, by the way, send you videos, pretty funny, interesting videos about statistics. People always make mistakes in probability, both in criminal investigations and in pretty much any other type of investigation. It's very, very difficult to realize what's true, what's not, and with statistics, even if everything is correct, so many ways to lead to misinterpretation. So we know that 20% of the population are left-handed. Okay. Now the question is, what's the probability that suspect is guilty given that this evidence is true? You see what we know that, right? So we know that given guilt, given that the person is guilty, he will certainly be left-handed, right? But if he is left-handed, that does not necessarily mean he's guilty. Yes. So how do we solve it? We have to really have a good representation in symbols, right? So in this case, it's not too bad. So G is the event suspect is guilty, right? So it's the property that assigns to each universe in which this particular guy is guilty. And we know that the probability is 0.6, and left is the event suspect is left-handed. We now want to know what's the probability of guilty given left-handed. Yes, given that you understand what I mean by left-handed. Left-handed means the event that the criminal is using his left hand for most purposes. Right. So what's the probability? G means not just somebody guilty. G means that this particular man is guilty, given that the guilty person is left-handed. Clear? So let's see how we do that. So then we say probability of, we can reverse it, right? So we just write it. And here we use that idea where we reverse it. We have probability that the the person is left-handed given that he is guilty. The probability that the person under investigation is left-handed given that he is guilty times the probability he is guilty, divided by the probability the person is left-handed, right? So the person is left-handed could be in two ways. Either the person is left-handed from being guilty, or the person is left-handed and innocent, right? So this is the situation where the person is, well, for certain, if he's guilty, then he will be left-handed, right? You see what we did? We reverse the conditioning, right? Everybody understands how I got to this formula, or do I need to fill in missing parts? Let me know. Yes, okay, let me explain how I reversed the formula. It's just what we did before, so it's like this. Here is how it's very important. So what we have is we have probability of guilty given left-handed is the same as probability of guilty and left-handed divided by probability of left-handed. Yes, that's what it means. So you understand what are those universes? Okay, guys. So I imagine that I go to universes where this particular person is left-handed, and the universes where this particular person is guilty, right? There are 60% of the universes where this particular person is guilty. Now, in how many universes is this particular person left-handed? You have to understand that's the question that's probability on the bottom. It's in how many universes is this particular person left-handed? Can you imagine that? Okay, good. So what happens next? Next, this is just the intersection of G and L, and it's much easier for me to condition it this way. So to write it as probability of the person being guilty times the probability of the person being left-handed given that he is guilty, divided by probability of left-handedness. I just break it apart. It means probability of left-handed and guilty plus probability that this person is left-handed and not guilty. Yes, that's the missing step that I haven't written. Are you following, guys, what's happening? What am I trying to do? And I'm not always doing it. And that's, of course, but I try to, whenever I truly deeply think about those questions, I try to imagine something. And this is what I'm imagining. I imagine that I'm observing universes. So we want to observe the many universes. And just imagine like you are, like whatever, Doctor Who, wherever else, traveling through parallel universes, Rick and Morty, I don't know, right? And you go to those different universes and you look at Jimmy Jones. And you look at Jimmy Jones and ask two questions. Are you left-handed? Are you guilty? Yes? So in 60% of the universes, you know that Jimmy Jones will be guilty. In how many of those universes will he be left-handed? Right? In how many universes is he, and if I'm just, and now here is the conditional probability that I'm asking. I am now only going to look at universes where he is left-handed. In those universes, how likely is he to be guilty? Understand? Among left-handed universes where he is using his left hand, in how many of those universes is he guilty? That's the question I'm asking, yes? And based on the information I have, I can calculate it this way, right? I can calculate the universes, the percentage of the universes where he is guilty, and then the percentage of the universes where he is left-handed, given that he is guilty. In all universes where he is guilty, he will have a left hand. He would use a left hand. Yes, primarily. Is that clear? So, and then you have this denominator. I need to calculate the probability that he is left-handed. So then I want to condition it based on the universes where he is guilty and the universes where he is not guilty. You understand? In some universes where he is not guilty, he will still be a left-handed person. Yes, it's possible. Clear? And then I just recondition this. So you see the denominator here is what I wrote here. Is it clear? I may erase my modification. Yes. Yes. Got it, guys? And think about all the time. When you do those questions, think of it all the time. So this is the situation that I was able to reverse. And then here is what I find. In all universes where he is guilty, he is always left-handed. And in the universes where he is not guilty, he is just an innocent left-handed person. And that means that there are 0.2 universes. 20% of the universes where he is not guilty, he is having a left hand. He's using a left hand. I'm sorry for my weird language. Good. And therefore, altogether, the probability that he is guilty, given that he is left-handed, is now 88%. That means that out of the universes where Jimmy Jones is left-handed, in 88% of them, he is also guilty. Yes? Is it clear? The next question is much more difficult. Are you ready for it? And it's so difficult that I wonder if it's worth mentioning. Because it is assumed in this question, for simplicity, Albert, it's assumed that that the guilty person definitely is left-handed. Understand? So it's known that basically this is a type of crime that could only have been committed by a left-handed person, for whichever reason, right? So that means that that if he is guilty, then he had to be left-handed, because only yes, makes sense. All right. So here is a generalization of Bayer's formula. So we don't always have to condition on one event and its complement. It's enough to have disjoint events F1, F2, F3. They can be even infinitely many of them, such that they partition the universe S, the set of all universes, into those disjoint segments. And then E is equal to the union of E and F1, E and F2, E and F3, and so on. Agreed? So what I'm saying here is very simply this. Maybe I should draw you a picture. So this is my set S. And suppose that what I want to find is the probability that E occurs. So this is E. I want to find the probability that E occurs. So what can I do? I can partition S not just necessarily into 2 segments, but let me partition it into several segments. So this is F1. This is F2. And maybe the remaining one is F3. Yes? So you see what happens here. So this is F3, F2, F1. Yes? So then what's the probability of E happening? Notice F1, F2, and F3 are disjoint. So the probability that E happens, either it's the universe is within this region, or the universe is in this region, or the universe is in E within this region. So in this situation, the probability of E is equal to the probability of E and F1 plus probability of E and F2 plus probability E and F3. Yes? Yes, Grant? Does it make sense? And this you can condition. You see, I can write this as the probability of E given F1 times probability F1 plus probability of E given F2 times the probability of F2 plus probability of E given F3 times the probability of F3. Yes? I can condition because maybe for some reason I know the likelihood of E happening within each region, F1, F2, F3. It just happens, as you will see in several examples, yes? So I can calculate the relative probability of this region to F1, relative probability of this region of E relative to F2, and so on. Right? So then that allows me to calculate the total probability. It's very similar to area. There, okay? So that's the generalized Bayes formula, and that's what we have here. And this is, it can go up to n, or the events could even be, it goes to infinity. You know, maybe I have F1, F2, F3 to infinity. Maybe the slices get very thin, and many of them, it doesn't matter, right? The point is that I can just use this type of conditioning. And here is one example of how that might be used. So imagine that a plane is missing, and it is presumed that it was equally likely to have crashed in any of 3 regions. And those regions are region 1, region 2, and region 3. Yes? And those regions are not all easy to search in the same extent. Some regions are very difficult to search. Some regions are very easy to search. Like imagine something crashes in a forest, maybe it's harder to find it, or in a mountainous area, much harder to find it, as opposed to like a field, big flat piece of land. Yes. So when you search a place, there is a chance that you will not find it, even if it's there. Do you agree? So that is determined, I suppose, statistically. So if you go, for instance, to my brother's room, the chances that you will not find something is very, very high, right? So BK represents the overlook probability. So if you search region 1, B1 will represent the likelihood of not finding something there, if in fact it is there. You understand? So imagine a very difficult region. If you search through it, your likelihood of finding something, even if it's there, is maybe 20%. In some other region, it might be 30%. They don't have to add up to 100. You understand? I mean, because if you're searching in this region, given that the item is there. So what is the probability that the plane is in region K if a search in region 1 is unsuccessful? Do you understand? So they searched region 1 and they did not find the plane. What's the probability the plane now is in region 1, region 2, region 3? Okay, so let's begin calculating it. So let R sub K be the event plane is in region K. And F1 is the event plane was not found in region 1. So I'm interested in, let's say, calculating probability R1 given F1, right? In other words, what's the likelihood that the plane is actually there, given that a search of region 1 did not yield a successful result? So I can recondition it. You see here I recondition it, I just do it fast. I just write it as probability F1 given R1 times probability R1, right? That's how you change this thing. All right, and then we will always probability F1 and probability of F1, I condition based on R1, based on R2, based on R3. Do you understand how I got this formula, guys? I just did that same thing that I did on my whiteboard just a moment ago, just I did it fast here, right? So I just have R1 and F1 divided by probability of F1, and then I rewrite the numerator as probability of F1 given R1 times the probability of R1 divided by F1 intersect R1, F1 intersect R2, F1 intersect, onwards, right? So because F1, I mean, not being able to find this object in region 1 depends on whether or not the object is there or not. If the object is not there, I will not find it. If the object is not there, I will not find it. If the object is there, I might still not find it. Yes. So it's an example where you want to do this type of conditioning. Here it is. And then look at it. I can erase probability R1, R2, and R3 because the probability the plane is there is 1/3. You agree? The plane is either in region 1 or region 2 or region 3, and is equally likely to be in any of those regions. So I can just cancel PR1, PR2, and PR3 from here, and I have this expression. Now, what is the numerator? The numerator means not finding something given it's there in R1. That's the probability that I will overlook it. So that's beta 1. Now, not finding in region 1, given that the plane is in region 1, it means I did not search properly. And of course, not finding the plane in region 1 if the plane is in region 2 is 1. And this is also 1. You agree? F1 given R2 or F1 given R3 is always 1. Because I cannot find something if it's not there, unless I am a philosopher. You know this joke, a philosopher is a blind man in a dark room with no windows searching for a black cat that's not there. Yes? Good, guys? So that what I have is the probability the plane now is in region 1 is B1 divided by B1 plus 2. Now, what about probability the plane is now in region 2 or region 3 if search of region 1 is did not do anything? Here the same exact question. I do that for K1 and K2, for K2 and K3, it's symmetric. So what do you have here? Of course, numerator is now 1. Do you agree? Numerator is 1, denominator is the same, because just that's the probability of F1. So it's 1 over beta 1 plus 2. And now, of course, you observe that it's bigger than beta 1, because beta 1 is a number smaller than 1 in general. It's always usually you will be able to find something if it's there. There is some chance, right? So beta 1, even if it's a very big number, it's still usually smaller than 1, at least not bigger than 1. So you can see that it's much more likely the plane is in a different region. Good. And here is one more example. So there are 3 flashlights in a bin. There is a type 1 flashlight, type 2, and type 3 flashlight. And here is the stats for them. So the probability type 1 works longer than 100 hours is 0.7. And you have 20% of all flashlights in the bin are of that form. Type 2 flashlight it's not as good. It works with probability 0.4 longer than 100 hours, and you have 30% of them in the bin. And type 3 is the worst of them all. It's only 30% likely to last longer than 100 hours, and you have 50% of them in the bin. Good. So question A, Now let's try to, let me give you an opportunity to calculate it. What is the probability that a randomly chosen flashlight lasts over 100 hours? Do you understand what I'm asking? So you randomly pick a flashlight. You don't know if it's type 1, type 2, type 3. And the question is, what's the probability it will last for more than 100 hours? Calculate, please. Yes, Gustavo, that's, I think, correct. Right. Let's do it together. Ready, guys? Or you want more time to think of it? Okay, you agree, that's nice. So here is the situation. So we have events A, B, and C, and that is type 1, type 2, and type 3 flashlights. So H is the event that the flashlight lasts longer than 100 hours. Now, it's hard to calculate this probability without knowing which type of flashlight I'm using, yes? So what do? So I know that if it lasts longer than 100 hours, then it was flashlight A that I picked, or flashlight B that I picked, or flashlight C that I picked, right? So in other words, if the universes in which the one flashlight I picked lasts longer than 100 hours, in each of those universes, I'm holding either type A or type B or type C flashlight. And that's what symbolically this here is capturing, yes? And those are disjoint events. So I can just add the probability HA, probability HB, and probability HC. And each of them I can condition. Because it's a probability of intersection of events, that's the probability of H given A times the probability A, plus probability H given B times the probability B, plus probability H given C times probability C. That's, by the way, one reason that it's some people don't write intersection. They write it like the two sets are joined, because it's very reminiscent of multiplication. You agree? Probability of intersection is kind of like multiplication of the probabilities. So in this sense. And the few people that responded, you are correct. This is the desired probability. You can see how you add it up, right? But it makes sense to you guys how it's calculated. Those numbers come from conditioning. I know the probability of lasting longer than 100 hours if I picked flashlight A. And I know the same probabilities for the other flashlights. So given that I have this flashlight, given that I know I'm in a universe holding flashlight A, I know 70% likelihood that I will do that, right? And then this is probability A, probability B, and probability. This is the portion of universes in which that actually happens. Yes? And then part B. Given that the flashlight lasted over 100 hours, what is the probability that it was of type 1 or type 2 or type 3? You know, so in other words, you already know that the flashlight worked longer than 100 hours. How likely do you think it's type A? How likely do you think it's type B and onwards? Well, 1 means that it's certain, Nicholas. Right? It's lasted longer than 100 hours. You cannot be certain it is, I think, the conditional probability that I picked flashlight number 1. It cannot be the same for each type, I think. Barry. Yes, well, that's Gustavo, you're correct. Think about it, guys. What am I asking? I am asking for probability A, given that the flashlight lasted longer than 100 hours. It does not guarantee that it was type A, because other flashlights could last longer than 100 hours. So there's no way the answer could have been 1. Function, well, I'm not sure what you mean by function there.
Meaning you do the same kind of calculation each time.
Yeah, very similar calculation. It's a bit annoying and repetitive, but you can see the numbers over here, and you can then, based on those numbers, see that it was most likely actually a flashlight of type C. Do you see that? Type C, which was the worst flashlight. Right? So a lot of people think that, or maybe would have thought that the probability is much more likely that you're holding flashlight A, because it's the best flashlight. But it's actually more likely that you were holding the worst type of flashlight. You realize that, guys? It's kind of like this question, who is, well, I mean, let's actually, let me not necessarily go there. So here, you understand how this calculation was carried out. It's probability of A given H. We already calculated H from the previous problem. So it's just probability of H given A times probability A, and similar calculations for all the remaining ones. And you can all see that it's 14 over 41, 12 over 41, 15 over 41. Yes? And then there is one little thing, hopefully, that will be useful to you, is another thing I want to emphasize to you guys. So just yet another way to emphasize why in many cases you can assume when you calculate probability more than you have, more information than you have. Just another example of it, right? So a lot of people delete information. Let's say toss 2 coins, delete the, if you're asked for probability about the first coin, delete information about second coin. I think in reverse. I think assume that in fact you know much more about the second coin. You understand? That's a difference in thinking. So people say if you toss 2 coins, and they are fair, what's the probability that first coin comes up heads? You say 1/2. And the way people say 1/2, they say, well, ignore the second coin, delete the information. And I say, no, the second coin landed heads. Let's calculate this probability, assuming second coin landed heads. If I say, I'm assuming that I actually know even more. Okay, now, how is that working? Let's say here is an example. Calculated the fastest way you can, guys, and then we will talk about it. So 1 of 4 fair dice will be chosen, and we don't know if there is a preference for one of them or not. Just we know that each die is fair. Make sense? I do not know that die number 1 will be chosen as frequently as die number 2 or as die number 3, right? So there are those 4 dice. I labeled 1, 2, 3, and 4. Blue, red, yellow, white, let's say, right? And the question is, given that the sum on the dice is 7, what is the probability that the numbers that came up were 1 and 6? Is the question clear? So the die is picked and you roll it twice, and then you calculate the sum on both rolls. What's the probability that if the sum is 7, that the outputs were 1 and 6? You can calculate and then let me know what assumptions you made. Very good, Gustavo. Yeah, one dice is tossed twice, and you know that the sum on both happen to be 7 on both tosses, right? And Chiara, well, I mean, you can calculate it so many ways, but yes, the answer is 1/3, and the answer is 2 out of 6, and what no, right? So so just yes. Now, one thing I would not bother you, Gustavo, or anybody else about Gustavo. You assumed you ignored the color on the die that was rolled, right? And the question is really, why did it not change the answer? You see, what we see, I do not ignore it. What I imagine is that the die that I was rolling was number 1. Same exact thing as what you wrote, Gustavo. It's a bit tedious to write yet another information about the die number, but I assume it was die number 1. Now, why is that correct? First of all, intuitively, guys, imagine that when you toss the die, imagine that once you begin tossing it, it's the same die that's being tossed. So you're either tossing it in the blue universes or in the red universes or the white universes. And within each of those universes, the die is fair. So the outcome is the same. So that's roughly what's happening here. But let's try to make it just precise, just to see what's really happening. You really develop intuition for that, yes? What's happening is there is the color of the die, and there is first row and second row. That's what's happening, right? For the first row, second row, that's my sample space in essence, right? That's the universe has to contain information about all 3 aspects. Yes, and let's assume that die number k is picked up with probability p sub k. Well, no, you're not confused, Gustavo, because you're solving everything correctly, right? It's just you have to be careful. That's what I'm saying, right? So don't always be too paranoid about anything, but be very careful. Is that some information in some possibly rare cases, when you toss it away, will end up giving you incorrect probability, right? And people that realize why, they are not that confused by this, right? They are not confused by, oh, but this is irrelevant. We saw examples, and one of them is in your exam. And every information is making the universe more particular. So you're zooming in on the particular universes where you are finding yourself. So the color of the die will do that. It just will not affect probability. That's all I'm saying. Now, why will it not affect probability in this case? Because of the following. So assume that die number 1 is picked with probability p1, die number 2 with probability p2, and in general, pk is the probability that I don't know with which die number k is picked. That's a sort of preference label, right? Probability, maybe one die is always preferred, or maybe there is some sort of indecision between 2 of them, right? So this is the situation, and of course the summation is 1 because one of the dice, one of them will be picked. And I want the probability that 6 and 1 occur given that the sum is 7. That's what I'm interested in, yes? If the sum is 7, what's the likelihood I had both 6 and 1? Now, what is this? This is the probability 6 and 1, and sum is 7 divided by probability sum is 7, yes? And now, how could I obtain sum 7? So I also have missing here some information. I break it up in a summation. It's either die 1, or die 2, or die 3, or die 4. Do you agree? So it's the same thing, but it's sum of 7 on die number 1, or sum 7 on die number 2, or onwards. Yes. You see what happens here? The summation, and on the denominator, I have the same summation. I condition, or I intersect with these joint events, die 1, die 2, die 3, right? To make it clear what's happening. And then what can I do here? And then I can condition each of them, right? So this is the probability that 6 and 1 and sum 7, given that die is k, the guy that was picked is numbered k, probability of this die being die number k. And same thing I do here. Yes, and now the crucial aspect here is that once I know which die I roll, it doesn't matter. It's going to be 6 and 1 and sum is 7, given that die is k, is the same as when die is equal to 1. Do you agree? So here is where I make the because the probabilities are not affected. Here is that when I make the assumption I was tossing die number 1. You see here, I switch for the summation. I switch k to 1 because the kind of die I'm tossing is not influencing the probability on this particular die. Yes? Do you see what I did here? And then this is just probability pk. And so look at it. This probability I can factor out. Do you agree? I can factor out the numerator probability. I can factor out the denominator probability, and I have this ratio. And this ratio cancels out to 1. And then what do you have here? Now this probability, so you see the probability that I'm talking about is yes, I'm talking about the probability of 6 and 1 and sum equal to 7, given die equal to 1 divided by the probability of sum is 7 and given that die is equal to 1. Yes. Now, you can either by set theory, you can also obviously see what it is. This is the same as the probability that 6 and 1 happen given that sum is 7, right? You can either break it apart in terms of sets and just see that it's the same as this condition. It's the same as this line here. So make sure that you either do that, maybe even both, that you can see that set theoretically, but you can also obviously see that this is true in general, right? So this is just like we know that it's you can just almost like by default assume that we have that extra box about the die number filled in, and we are now working with a universe where the only unknowns are what's the sum in general and which outputs on first row and second row, right? So this is the same thing as the conditional probability that 6 and 1 were rolled given that sum is equal to 7, and of course that the die is number 1. Yes, think about it, guys. You should be able to manipulate it symbolically, but I hope you're also able to see that in general, right? Because you're always, when you're introducing extra conditions, you are just adding what is the background, what's the default, right? Default is really that we have the die rolled is 1, and that gives us the probability 1/3. Good. All I'm trying to show with this example again, guys, is that to try to change your thinking in general, that when you are ignoring some information, you're ignoring because you're assuming it's very definite, not because it's irrelevant, but because you were able to say exactly this happened. And that doesn't affect the probability. Yes. Good. So then let's move on to curious problems. So let's do this one. So this one involves, I hope you would like them. It's an assortment of problems. So a mathematician likes to drink his tea with rum, and he does it as follows. If he has 2 beakers, one beaker contains rum and the other beaker contains tea. For our purposes, we'll just say it's a glass of water. And then when he does, it takes tea, and then from that gap that results from him removing some molecules of tea, he pours in the rum until, again, the beaker is full again, and then he stirs everything, right? And the question is, what's the probability that his very last sip will be that of tea? In other words, the very last molecule that he drinks is tea. And how do we understand this question? Imagine that drinking involves sampling one molecule at a time, okay? Just for simplicity. So here is the situation when you have 3 molecules of T and 3 molecules of RAM. Yes. So what's going to happen is that first you remove one blue molecule, and once you remove it, you replace it with one red molecule, right? And then you have a bunch of blue molecules and red molecules. You remove one molecule always from the beaker labeled T. And whenever you still have something, you replenish it with a molecule from the other beaker. Yes? So far, so good? So the question is, what's the probability that the last molecule removed is either molecule 1 or molecule 2 or molecule 3? If you have only 3 molecules in each beaker, yes? So you can see it over here. So we're going to do it a bit faster here. So probability that that the last molecule is initially from the beaker T, it's the probability that last molecule is 1 or 2 or 3, and by symmetry, it's just 3 times the probability of T1. Do you agree? It's 3 times the probability of T1 by symmetry, because it's either the last one is, if the last one is T, then it's either T1 or T2 or T3. Yes, so we just need to calculate 3 times probability of T1. And then how do we do that? So now I just focus on molecule 1 and I calculate the probability that it survives to be the very last one. So it cannot be the first molecule removed, that's first sample. Yes, its probability of survival is what? If the molecule is picked randomly, what's the probability of surviving first round? 2/3. Very good, Nicholas, right? So it means it's not picked. Its likelihood of not being picked is 2 out of 3. Do you agree? First round. Now, one molecule was removed and replaced it. Now, again, it needs to survive second round. To survive second round, again, it's 1 out of 3, so it's 2/3, right? So how many rounds will it survive? You can see that you can just see that by playing this game. Remove and replace until you have nothing to replace. So it will survive. You would say up to the 3 rounds. After 3 rounds, there is already no replacement coming, right? So surviving 3 rounds means 2/3 times 2/3 times 2/3 to the power of 3. Do you agree? This is how many rounds surviving until there are no more replacements from the RAM beaker. Yes, from the red beaker up to this point. So you see, it's 2/3 times 2/3 times 2/3. Yes, agreed? 2/3, 2/3, 2/3. So once you're in this situation, it's 2/3 cubed. Now from this situation, surviving it again 1 more round is again 2 times 3, and then surviving it again is now 1/2. Right? Did you see what happened here, guys? Here it is. 3 times 2/3, 2/3, 2/3. That's first sampling. They survived second sampling, third sampling, then fourth sampling. When they survived first 3 samplings, that's when there was still replacement. Now here, fourth sample is when no replacement is coming anymore. So then when 1 molecule is removed, there are now 2 molecules, and its likelihood to survive again is 1/2. So the answer is, when you simplify everything, look at it. There is this 3, there is 2 and 2 cross out, and then you have this 3 and this 3, they cross out, and it becomes 2/3 cubed. Are you with me? 2/3 cubed. Now you can play this game, and you should convince yourself that when you have 4 and 4 molecules, then the probability that last one to be removed is from the initial beaker, from beaker T. It was going to be 3/4 to the power of 4. If you have 5 and 5 molecules, it will be 4/5 to the power of 5, and so on. And in general, this probability, this is going to be the probability is when you have n molecules, where n is a large number, it's going to be n-1 over n to the power of n. What is the limit of this, please? So if n is very large, what is this number similar to? So it's n minus 1 divided by n all to the power of n. Yes, Barry, very good. Camille, exactly. The answer is this limit is e to the minus 1. As n is larger, you will get e to the minus 1. And you're right, Barry, it will decrease to that limit, right? So it's not 1/2, it's slightly lower than 1/2. And the reason it's slightly lower than 1/2 is that the molecules are initially exposed in the first sampling, and T is the first to be sampled. So their survival rate is slightly less than the survival rate for R. You understand? It's like you're first in action, you're longest in action than in war, for instance, right? So your likelihood of survival is less, perhaps, for that reason. Good. Well, yes. Well, I mean, it's all related, right? So you all see that, guys. Just play with this example. It's easy to convince yourself. Once you just play with just a few numbers, you can see that this is the limit you should get. And then here is another question. I'm not sure if we this one is the involved one that I was thinking about. I'm not sure if you will enjoy it. So imagine a jewelry store was burglarized on Madison Avenue. Something was stolen, and we know that there is exactly one perpetrator, and it's one of n suspects. Maybe some camera recorded all the people that came into the store, and exactly n people came to the store. Yes. So initially, of course, there is no bias to who was the thief. There is no better information. They all kind of are twins, as far as we know, and the probability it's any one of those culprits is 1/n. But then you have extra evidence, right? So for instance, so the extra evidence is there is an eyewitness testifying that, well, the person that stole the jewelry was driving a black car, and the person is certain of that. The person that stole the jewelry just drove a black car. Good. Now, some innocent people drive black cars. You agree? It could happen that the person that drove the black car, I mean, you understand, if a person drives a black car, does not make him guilty. Maybe it was just some Uber driver. So P0 is the probability that an innocent person drives a black car. That might be, I'm not sure how you calculate it. It could be just the ratio of black cars that are being driven among other cars that are all together, right? So P0 is just the likelihood somebody from the population happens to drive a black car, and maybe there's nothing special about driving a black car, right? And then assume that that the reliability of the eyewitness is P1, which is higher than P0. Reliability means how certain is that the evidence is true. In other words, the person is adamant, well, the thief definitely drove a black car, but maybe the witness is prejudiced. And it could be that that the witness did not really see something correctly, remember something incorrectly. You know, people are very confused. So P1 is, I'm not sure how to estimate P1 really, but it's some sort of measurement of how reliable is this witness. Yes? So, but we're assuming that that it's higher than average. Understand? Okay, meaning that we are more likely to think that that black car indicates increases the probability of guilt. That's what I mean. Yes. It's an evidence that's increasing the probability of guilt, but not making it so the guilty person might still not be driving a black car, so to speak, right? But it's much more likely that the guilty person is driving a black car. Good. And we have those ratios. A is the ratio of P0 over P1, and B is the ratio of 1 minus P1 over 1 minus P0. Okay. And then hopefully you remember some of those things. I'll remind you of them later. So suppose now we have a camera evidence. So after listening to the witness, the investigators look at all the videos and they observe that that this Vasya Voronov was leaving the store and entering a black car. Yes? Do you understand what I'm saying, guys? So there is a camera and it shows that some guy, and they identified him as is one of the suspects, and he is indeed entering a black car. And the witness said the guy that stole something was going into a black car. Yes? Now the question is, what is the probability that he is the criminal, the perpetrator? Okay, so then let's try to solve those questions. So we're going to assume, given that he drives a black car, that's exactly right. Right? What's the probability he's guilty given that he drives a black car? So let's label those events for future. I'm going to I want to just in general indicate G by GK, where K is 1, 2, 3 is the event that person number K is guilty. So it's either person 1 all the way to person number N, and Gn, in the nth person is Voronov. The nth guy I'm going to label as Voronov. That's this guy. So Gn is him. So I want, and for each of the perpetrators, I want the event they drive black cars. So each of them could have been driving a black car. You agree? So Bn indicates the nth person drives a black car. So I want guilt of the nth person given that the nth person drives a black car. So far good? And what do we get? So here is my probability. I just calculated. You see, guys, I calculated. Bn given Gn, probability Gn, probability Bn given Gn, probability Gn. You know, this is a standard calculation, and this is what I get, right? Probability Bn given Gn, it's P1. It's the eyewitness's probability. Understand? The eyewitness. What is the eyewitness doing? Can you imagine it? It's a bit harder than before. The eyewitness is making a statement about universes, right? So she is saying that with probability P1, in other words, let's say if P1 is 80%, right? It means that the guilty in all the universes where the particular person is guilty. She doesn't know if it's Vasya, she doesn't know who it is, right? But in all universes where a particular person is guilty, 80% of those universes, that person drives black cars. That's what we mean by reliability. Are you clear? So you have to really imagine that, right? Because otherwise what a witness says is very difficult to comprehend. But she's saying that in 80% of the universes a given person is guilty, he is driving a black car. In 20 of those universes, he is guilty, but driving some other car. Understand? Of all the universes where the particular person is guilty, yes? So that's when I condition it. So given that Gn is guilty, what's the probability? I reverse it, right? Given that he is guilty, what's the probability he will be driving a black car? It's higher than in population. Innocent people don't do it as frequently, right? So it's P1. Now, what's the probability he will be driving a black car if he is not guilty? That would be P0. The usual, that's the non-guilty people driving black cars. So P0 represents the likelihood of non-guilty people driving black cars, yes? And then when I calculate this ratio, this is what I get. Yes? Do you follow, guys? Now, let's do, if you are willing to wait, let's finish this question. Let's do part B. So further investigation, yes, they looked at all the people, not just at Vasya, but they found that he is the only one among the N individuals that actually drove a black car. Understand? So the witness says the criminal escaped in a black car and no other person escaped in a black car other than this guy. What's the likelihood he is guilty now? You see? So it's much more damning evidence. Do you agree? Should be more damning. So here is how you mark it. You see, guys, that's why I had those things. So here is the new situation. The new evidence is that everyone is not driving a black car, and he's driving a black car. Yes? This is how I decided to label it. So 1 does not drive a black car, 2 does not drive, and I want to know the guilt, the probability of guilt of the nth person, given that he is the only one driving a black car. So I have this, when I condition, I have this divided by that. And then let's calculate the numerator. The numerator is just a product. It's probability of Gn times probability B1 complement given Gn, right? So what's probability of Gn initially? It's 1 over n. What's the probability of first person not driving a black car given that the nth person is guilty? It's 1 minus P0, or P0 is the, so innocent people don't drive black cars with probability 1 minus P0. Now, what's the probability that person number 2 does not drive a black car if person number n is guilty? All right, it doesn't matter what other people do. So let's say, imagine that it's independent. If say person 1 does not drive a black car, it will not affect person 2 driving or not driving a black car. So that would, all of those things will be 1 minus P0 to the power of n minus 1. And then, of course, the last evidence, given that the person is guilty, the probability he drives a black car is P1. So this is the probability we have. And then I calculate a similar number for the denominator. And this is and this is what we get. For the denominator, look at it. The probability B1 complement, B2 complement. I need to condition that on who is guilty. You see, to understand that, I need to know who is guilty and who is not guilty. So in this case, there are many people that could be guilty, either person 1 or 2 or 3. And that's what I do over here with the summation. I condition on who is the guilty person. Is it person 1, person 2, person 3, and onwards? And I isolate person number n. We already calculated this probability for person number n. It's this number. And everything else, it's a symmetric probability, right? It's very symmetric. Is it person 1 guilty or 2 guilty or 3 or n minus 1? It's the same as n minus 1 times the probability that person 1 is guilty and everybody else is, person 1 through person n minus 1 is not driving a black car, and the last person is driving a black car. So when you calculate this, again, this is what you get, right? This is where this part in this red box, this is what you get if you calculate it. So make sure you can figure it out. I'm rushing a little as I figure you want to go home, right? I feel bad holding you beyond your time. Yes? So think about it. It's an interesting question. In fact, maybe read the question by yourself and try to solve it. See if you can actually come up with a similar solution. And then here is what you get. Once you simplify everything, you get this number, which you can be, in terms of my labelings, you can simplify as this fraction. All right, guys. So again, I would like, I'm hoping you are going to open this particular question and see if you can look at this question, this exercise, and solve it. And not just because of the algebra, but because you really want to train yourself to think very precisely, right? What is an eyewitness? Doesn't matter if it's true or not, but what is an eyewitness? What is it that they are speaking about when they are imagining universe? You understand what is eyewitness saying with what probability? It's like, I think 80% likely the person was 6 feet tall. What does it mean? It means that if the person is guilty, in all the universes where the person is guilty, in 80% of those universes, the person is 6 feet tall. That's how I imagine it. If I don't do that, I don't understand what it means. Yes? So, all right, guys, thank you for staying and being so patient. Good luck with the exam. I hope it's just hard for you, enough for you to improve. Yes, guys, and if you're staying, let me know how I may be of assistance to you. I'm going to stop the recording.